Hey, Calc kids. Today we're looking at the derivatives of the inverse trig functions on Calc with Mr. Forbes. Notes out, we're on section 3.8 and away we go. So recall we talked about inverse functions back in college algebra and a little bit in pre-calc. So recall that an inverse function produces another function. So we're going to keep that in mind as we look at the derivatives. The inverse of a function produces another function. For the most part, we're going to just deal with functions that do that. So we have the statement, if a graph of a function has no cups or corners, then what is true of its inverse? Well, then the inverse is also differentiable. So we can also take the derivative of the inverse functions. So before we start, remember that we have inverse functions. And so we have sine inverse of x is equal to y. Remember, we can flip that around to flip-flop the argument and the value to say then sine of y is equal to x. And also recall that in trig, we learned that sine inverse is actually called the arc sine. It's called the arc sine. Here we go, theorem 3 then, the derivatives of inverse functions. If f is differentiable at every point of an interval I, and we talked about in trig, or we would have talked about in trig, except for pandemic, what interval would work to make a inverse trig function. Df dx is never 0 on that interval. Then f has an inverse, and f inverse is differentiable at every point on the interval f of I. So wherever we define that interval for the trig function to be a function, the inverse to be a function, then it'll be differentiable. So let's look at deriving a formula for y equals sine inverse of x. Again, the derivative inverse for arc sine is what this is. Well, first we're going to use our trick, and we're going to say that basically we're not going to take the derivative of sine inverse, we're going to take the derivative of the inverse. So we're going to flip-flop these to say x then is equal to the sine of y. Now we're going to take the derivative of both sides. So we're going to do our implicit differentiation to both sides is basically what we're going to do. And so what happens? Well, we know the derivative of x, that's easy. That's got to be 1. We're going to use our implicit differentiation for derivative of sine of y. Now this is chain rule, so we're going to take the derivative of sine of y. The derivative of sine of y is cosine of y. Then we have to take the derivative of the inside, which is the argument. The derivative of y is 1, but because we're taking the derivative with respect to x, that has to leave us with a dy dx. Well, then, following our implicit differentiation rules, we're going to solve for dy dx. And so we're going to divide both sides by cosine. That gives us 1 over cosine of y. And we're going to remember, and here we're going to insert a trig derivative. And you're kind of like, why are we going to insert a trig derivative or trig identity? But we are. So we're going to recall that in trig, so from trig, we remember that x squared plus y squared is equal 1. And we remember that x squared and cosine squared is the same as x and y. So sine squared of x plus cosine squared of x is equal to 1. In this case, y, we could have used the same thing. So we're going to solve for cosine. So cosine squared of x then is equal to 1 minus sine squared of x. And that gets us then cosine of x is equal to the square root of 1 minus sine squared of x. But remember, sine is also the vertical, cosine is also the adjacent, the x. So we can actually just call this 1 minus x squared, the square root of 1 minus x squared. And we're going to plug that back then into our cosine. All right, so we're going to call this, well, we'll call this cosine of y because that's what's matching our formula. And so we're going to plug that back in. So that gives us 1 over the square root of 1 minus y squared is equal to dy dx. And finally, then we're going to set this up then as our formula. So here's our derivative, the derivative dx of the arc sine inverse, and I'm going to call this u, so we can put in a chain rule built into this, is equal to 1 over the square root of 1 minus u squared, and then whatever that u argument is, we have to take the derivative of it as well, using our chain rule du dx. So there's the derivative for arc sine. So let's look at an example of that. And we're also going to add these to our trig note cards as well, or derivative note cards as well. So we want the derivative of sine inverse of x squared. For that, we're simply going to use our formula. So this is 1 over the square root of 1 minus, the argument is x squared, quantity squared. That's all inside the square root, times du dx. That's the derivative of the argument, which is 2x. We want to simplify that. 2x will go to the numerator. We still have the square root in the denominator, and that's 1 minus x to the 4th. So there's the derivative formula for arc sine of x squared. Next, let's look at driving a formula for the derivative of arc tangent. So this is arc tan. We're going to recall, again, we're going to flip this around. So flip the x's and the y's. So that's x is equal to tangent of y. So we take out the inverse. We're going to take the derivative of both sides. So the derivative of x is 1 again. The derivative of tangent, recall, is secant squared of y. And then because we took a derivative of we have to take the derivative of the argument, which is 1. But because it's a y, again, we need a dy dx. We're going to solve for dy dx again. And that gives us 1 over secant squared of y. All right, what are we going to do with that? Well, we're going to recall that secant squared of y is an identity. We're going to plug in a Pythagorean identity there. And that is 1 over secant squared is 1 plus tangent squared of y. And then we're also going to notice, if we go back to this equation, right, we take x is equal to tangent of y, and we actually square both sides, we get x squared is equal to tangent squared y. Well, there's a tangent squared of y, there's x squared. So this is 1 over 1 plus x squared. So here's our formula for the derivative of arctangent. The derivative, d du, of tangent inverse. And again, we're going to put in a u here. So we have a built-in chain rule to help us out. That is 1 over 1 plus u squared du dx. And again, we're going to add that to our derivative note card. All right, let's look at an example for that. A particle moves along an x-axis so that its position at any time t greater than or equal to 0 is x of t is equal to the tangent inverse of square root of t. What is the velocity of the particle when t is equal to 16? So let's review. This is our position function. And our position function is d dx, tangent of inverse of u. And that formula again is 1 over 1 plus u squared du dx. And so we want the velocity. That's the first derivative. So we want dy dx. And so we're going to take the derivative. And we're going to plug in what we know. Our argument u is the square root of t. So this is 1 over 1 plus square root of t quantity squared times the derivative of square root of t. That's t to the 1/2. So that's 1/2 t to the negative 1/2 when we subtract 1. All right, so again, another way we could do that is we could write down what is u. U is the square root of t. So du dt, the derivative of u with respect to t. Again, remember that's t to the 1/2. 1/2 comes to the front, that's t to the negative 1/2. And here's our velocity formula. And we know we want to evaluate this at t equals 16. So let's plug in our 16 for all of the t's. It gives us 1 over 1 plus square root of 16 squared times 1/2 times 16 to the negative 1/2. And we'll follow all that through. Square root of 16 is 4. Square root of 16 plus 1 is 17. So that first part is 1/17. These are all multiplied times 1/2. Square root of 16 to the negative 1/2 is 1/4. And we'll put that on a calculator. And we get 1 over 136. So there's the velocity of our particle at t equals 16. Then the next one we're going to look at, actually the kind of the last one we're going to look at is secant inverse. So this would be arc secant, and we're not going to drive this one, but ddx of secant inverse. Again, we're going to use our built-in chain rule here with the u is going to be this function, 1 over the absolute value of the argument times the square root of the argument squared minus 1. We multiply all of that by du dx, the derivative of the argument. Let's look at an example of that one. So find the derivative of secant inverse of 5x to the 4th. So again, we're going to plug into our formula. The derivative of secant of inverse of u is equal to 1 over the absolute value of u times the square root of u squared minus 1 times du dx. All right, so what is our u? Our u is 5x to the 4th. And so we're going to plug in, and here we go. So we have 1 over, our u is 5x to the 4th. So our du dx is 20x cubed. So plug in what we have. So 1 over the absolute value of 5x to the 4th times the square root of 5x to the 4th squared minus 1 times 20x cubed over 1. All right, now we want to see if we can simplify. The absolute value of 5x to the 4th is just 5x to the 4th. That will simplify. 5 and 20 simplify, leaving 1 and 4. X cubed will simplify with the x to the 4th, leaving 1x. And so we have a 4 left in the numerator. There's an x outside the square root. Inside the square root, we're left with 5x to the 4 squared. That's 25x to the 8th minus 1. And again, we'll stop there. For the other three, arc cosecant, arc cotangent, and arc cosecant, recall from trig that cosine inverse of x is equal to the pi halves minus sine inverse of cox, right? These are co-functions. Cotangent is equal to 90 minus tangent inverse. Cosecant inverse is equal to 90 minus secant inverse. Therefore, because they're opposites, their derivatives are just the opposite. So the derivative of cosine inverse is negative 1 over square root 1 minus u squared du dx. The derivative of arc cotangent is negative 1 over 1 plus u squared du dx. And the derivative of cosecant inverse is negative 1 over the absolute value of u square root u squared minus 1 du dx. And again, we're going to add all of those to your note card. A couple more examples. So find the derivative for y is equal to z cosine inverse of z minus square root of 1 minus z squared. All right, so we have y prime. And we need to notice, what do we need to notice? Well, we're multiplying a variable times the cosine. So we're going to have to use the chain rule on that one. For the derivative of this one, it's separated by minus. So we can just take derivative of that using regular chain rule. Remember, this would be minus 1 minus z squared to the 1/2. And so here we go. So for a chain rule, we'll take the first times the derivative of the second. So that's going to be z times the derivative of cosine, the cosine inverse or arc cosine. So that is -1 over square root. We're just plugging in from the formula. 1 minus the argument is z. So that's just 1 minus z squared. Plus, now we're going to do the other one. So cosine inverse or arc cosine of z times the derivative of z, that's just 1. And so we get plus the cosine inverse of z. Now we'll tackle the last term. And for this, we have to use the chain rule. So the 1/2 comes down, so minus 1/2. The square root stays the same, so square root 1 minus z squared times the inside. The derivative of 1 is 0. The derivative of negative z squared would be -2z. And we'll look and see, does anything simplify? Well, here we get, this is -2 over square root 1 minus z squared plus cosine inverse of z. Here the -2's and the negatives cancel, leaving us a plus. That was a -1/2, so I should put that as a -1/2. That's a 1 over. I missed that part. When we subtracted the 1 from 1/2, that should have been a -1/2, making that a denominator. So that, what are we left with? I can't even read my writing. That's a z, not a 2. So this was a z. Here the 2's canceled, the z did not. So we have z over square root 1 minus z squared. That's what we're going for. Then what do you notice about the minus z over square root of 1 minus z squared plus z over square root of 1 minus z squared? That's right, they cancel. So our final answer is cosine inverse of z is our answer. And last one, example 5, find the derivative for y equals arc secant of 2x cubed. Let's recall the formula for that. The derivative of arc secant of u is 1 over the absolute value of u, square root u squared minus 1 du dx. And so here we go. So the first derivative is equal to, we don't have anything else to worry about in terms of chain rule or product rule, so we can just plug into our formula. Notice u is 2x cubed, so du dx is 6x squared. So we're plugging into our formula. So this is 1 over absolute value of u would be the absolute value of 2x cubed times the square root of 2x cubed squared minus 1 times the derivative, which is 6x squared. From there, we want to see if we can simplify anything. We note that the 2 and the 6 will simplify. This cubed, we have to leave inside absolute values because we don't know if the x is positive or negative. So this is an absolute value of x cubed. If it was even, we could get rid of the parentheses because that will guarantee it's going to be even or positive. But because this is an odd exponent, we don't know if this term is going to be positive or not. So we have to leave the absolute values. I should have wrote that further down. So we have absolute value of x cubed, square root, square the inside, that's 4x to the 6th, minus 1, and we still have a 3 in the numerator. Homework assignment for inverse trig functions is 3-8, page 170, 1 through 8, and 13 through 22. Have a good day, Maroons.